In this video, we're going to look at tangent planes, and then we're also going to take a look at the second derivative test in multivariables. So, first of all, remember we need a point. So we plug 3, 2 into this thing, and I guess 3 cubed times 2 would be 54. So I'm just going to put. I don't even need this. I'm just going to put equals 54. So we've got 3, 2, and 54. Now the slope. Well, I need to know the slope with respect to x. So treating y as a constant, I just have 3x squared y. Evaluating that at 3, 2. Well, 3 times 9 is 27 times 2 is 54. Partial derivative with respect to y would be just x cubed. Evaluate at 3, 2. So this is 27. So my tangent plane would be z equals point plus the x slope, and then x minus the x coordinate plus y slope, and y minus the y coordinate. Just like that. There's my tangent plane. All right, the next one. The point piece of this. Plug in 1 and negative 2. So 1 cubed plus negative 2 squared, so it's 5. So partial derivative with respect to x. So 3x squared. Evaluate at 1 and negative 2. So this is just 3. Partial derivative with respect to y is just 2y. Evaluate at 1, negative 2. This is negative 4. So, that point. Three, and then x minus the x coordinate. And y minus the y coordinate. And there is your tangent plane. Now, looking back at Calc 1 and 2, it says when we want to find the maximum or minimum or a horizontal tangent, must be true. And I hope you remember that that means that the derivative had to be equal to 0. Well, it's not any different now, except now we're talking 3 dimensions. So we're looking for a spot where both with respect to x and with respect to y are equal to 0. Okay, so let's try one. So, first of all, we're going to find the derivative with respect to x, so treating y as a constant. So 22x minus 2y. That'll do it. Derivative with respect to y, so treating x as a constant. I've got negative 2x plus 4y plus 3. Now, I've got kind of a system here of equations. What I could do, because remember I'm trying to figure out where there's 0, so I could do a little substitution. Maybe say that 22x equals 2y, so y is equal to 11x. And then I could substitute that in here. So I could have negative 2x plus 4 times 11x plus 3 equals 0. So negative 2x plus 44x plus 3 equals 0. Which means that 42x equals negative 3, so x is negative 3/42 or negative 1/14. And of course, I go back here and I say, well, I know that y is 11 times that, so y is negative 11/14. So there is my critical point. It's where both derivatives are equal to 0. Now, I would like to be able to classify that. And there's really not a great way to do it like the way that we did before where we could do sign analysis. Now we need something else. So the second derivative test looks like this. We calculate something that's usually referred to as D. And it is the product of the second derivative, or the second partials, f and x, with x both, with y, taken with y both, those product, minus x then y squared at that point. Okay, so let me kind of put this down. I'll bring this back up. We need to calculate those partial derivatives. So f(x)(x), well, that would be taking this one and doing it again with respect to x, which would just be 22. F(y)(y), so that would be taking this one and again treating x as a constant. So this answer would just be 4. Now doing x and then y, well, we already have the x, right? That's this one. This is with respect to x. Now we do this one with respect to y. Well, that means this would be a constant 0, so this is just -2. So now plugging this into this formula that says d is this times this, so 22 times 4 minus -2 squared, so 88 minus 4 is 84. Now I'm just going to pull this up. So here's what it says. If d is positive, and it is, so d is positive, and let me put, so those two, because d isn't negative and it isn't equal to 0, and this derivative is positive, which it was, it's 22, then we have a minimum. So that's what we had, was a minimum. And I did provide the graph, so I mean you can see there is a minimum there. Okay, let's try one more. Okay, so with respect to x, so we treat y as a constant. We've got 3x squared minus 3y, and with respect to y, we've got -3x plus 3y squared. We're setting them both equal to 0. So we could pick one. Okay, maybe picking this one, we'd say 3x squared equals 3y. So divide both sides by 3, we could say that y is equal to x squared. So when we see the y, we can replace it with x squared, so this would be x to the 4th, like that. So factoring a -3 out, maybe -3x, I'd have 1 minus x cubed. So x is either 0 or 1. So that means that y is either 0 or 1. Okay, so we got a couple of points to check here. We've got 0, 0, and we've got 1, 1. So now we need these second derivatives to do some analysis. So let's do respect to x again. So I'm just going to go back up here and go again. So this is now a constant. So the derivative is just going to be 6x. With y, it will just be 6y, and x comma y, so I take the x one, and now I do it with respect to y, so this is a constant, so it is just -3. Okay. Now I actually should evaluate. Let's start with 0, 0. Okay, so obviously I end up, if I evaluate that at 0, 0, I end up with 0, 0, and -3. So I've got, according to the test, remember what d is. I'm just going to put this right here. D is the product of the two derivatives with respect to x, and y, and then minus that kind of mixed one squared. So I've got 0 times 0 minus -3 squared, so I've got -9. So you see right here it says if d is negative, we have a saddle point. Okay, so this is a saddle. Now if I plug in 1, 1, I get 6 and 6 and -3. So this one I'd have 6 times 6 minus negative 3 squared. Well, 36 minus 9 is 27. So now we have a positive answer, and therefore we have to do a little bit more. We say, okay, so we had a positive d, and our derivative, this one, was 6, so it is a minimum. Okay. Now, again, I have the graph up here, and maybe you can see that, in fact, we do have a minimum right there. And the scale's a lot, but that is the minimum. And this point, kind of this curved in point, this represents the saddle, because it's not a max or a min. So there's a min, and there's our saddle.